Hello, everyone, and welcome to our webinar on Advanced Aqueous Geochemical Numerical Modeling. My name is Martin Drager. I'm with Water Services and Technologies located in Canada. And today with me is Mariana Verla from our office in Brazil. Now, a little bit about Water Services and Technologies. So the company was founded in 2017. Our current CEO and president, Nilsen Gerger, was the one founding the company. And some of you may be aware of Nilsen. He was the president of a famous company in Waterloo called Waterloo Hydrogeologic that developed a number of software applications and provided technical services for water. You may recognize Visual ModFlow. Nilsen was the author of Visual ModFlow, as well as co-authored FlowPath 2, Airflow SVE, FlowNet Trans, and was the visionary of HydroGeoAnalyst and Visual Pozos. So Nilsen, we really appreciate him as a leader of our company, providing innovation and expertise in groundwater and water management. Now, the company does focus a lot on and provide services to the mining industry, but we also provide services in other sectors, including water resources. We're talking about public water supply, food and beverage industry as well as water sanitation, industrial, and energy clients, all related to water resources management and core data management. Beyond our offices in Brazil, which we have two in Florianopolis and Belo Horizonte, we opened an office in Kazakhstan really to meet the demands of mining in 2022, and quickly, or shortly after, recently actually, opened an office here in Canada. Now, who are we? We're a technical organization with a number of earth sciences and engineering personnel on staff with focus in hydrogeology, hydrology, hydrogeotechnical, aqueous geochemistry areas of expertise. Plus, we're offering services in water audits and digital services. So really, our team is comprised of multidisciplinary teams that really is required when dealing with complex water resources challenges at mines. Outside of the direct team of technical experts, we have an entire office supporting all the works behind what they're delivering. We have a project management office and a data management and GIS group that supports all the activities that we do in delivering projects around water resources. And sometimes we don't have technologies that help us to achieve a solution. So we occasionally will develop our own technology. You'll notice here Visual Water Balance and the WST Fielder. We actually did our first webinar on Visual Water Balance, which is a really new approach to making sure that we have a dynamic accounting of water on the site and how it moves and changes. And it's a very impactful tool for planning water resilience and just daily operational, identifying daily operational risks. WST Fielder is a handheld application that we developed in-house so that our customer could achieve their result. We do work with a number of technologies, best-in-class technologies to deliver projects. I'm sure some of you may be familiar with some of these products, but we also offer software and sensors in the event that you need some. We do sell those as a company, and we offer academic academy, which is a combination of webinars, courses, and workshops that help really our customers and others learn about our industry, about the new approaches to addressing water resource challenges. Our projects, so we focus obviously on water resources management, and that's a wide spectrum of types of projects. We're very familiar, and we do a lot of water balance assessments. Mine dewatering, obviously, in the mining world is a big one. Aqueous geochemical modeling, which Mariana will share with you all the insights to that today. And moving down the list to subsurface characterization, environmental data management, and more recently, the ESG KPI automation and reporting, which has helped a number of people, customers save time and money. And speaking of saving time and money, here's just a small sample of some of the customers that we're helping globally. Some of the savings in time and cost example, we saved one client $40 million when it comes to data management and reporting costs. In terms of time, we've saved 90% time savings when it came to compliance reporting. And this is really through our data management group and digital services group. And we've also, on the technical side in the field, we've helped operationally save up to $120 million in terms of my dewatering optimization. So we're really trying to help each of our clients not only reach their operational goals, identify risks and save money, but really help them reach their ESG goals as well. So the goals of the webinar, we really hope that when you leave here, that we're providing you with insights into the applications of aqueous geochemical modeling and for mine water quality management. And we're also hoping that to demonstrate some examples and strategies on how you can apply numerical modeling to help predict future water, wastewater concentrations in mining. So a little bit about Mariana. So Mariana is an expert in geochemistry with an emphasis on igneous petrology, and she's an expert in acquisition and interpretation of geochemical and isotopic data on minerals and rocks. And obviously around aqueous geochemical numerical modeling, she'll be talking a lot about that today. She holds degrees in Masters in Science from Stellenbosch University and also the University of Federal do Rio Grande do Sul. So I expect you're going to learn a lot in this next part of the session. So the question is, where do we start? And Mariana, I think you have some answers to that.
Thank you very much, Martin. So hello, everyone. I am Mariana, and I hope you enjoyed this presentation. And well, why aqueous geochemical modeling is an important aspect in mining operations. So the mining companies, they are committed to managing water quality to reach the ESG goals while conducting mining operation effectively. And one of the challenges faced by the mining industry at a global scale is to properly manage its wastewaters, tailing, and other residues with high potential for chemical load release. And part of the decision-making process in wastewaters and tailings management involves the possibility of predicting future concentration and discharge rates. And this allows proactive measures and controls to be taken. So, in this context, the numerical modeling is a powerful tool to estimate future concentrations, considering different scenarios and associated uncertainties. So, when we are looking for the wastewater management, we should consider different steps. We should consider the diagnosis and prediction and also the solution. And in this specific presentation, we will focus on prediction, with the aqueous geochemical numerical modeling being an important part of this subject. And well, in this context, our vision is aligned with the guideline and best practices in the mine industry. And here, for example, we have demand, which among its main reports deals significantly with the prediction aspect. And well, speaking about the prediction methods, we can cite the laboratory and field testing and also the numerical modeling. And well, it's important to mention that both they should be performed based on an adequate conceptual understanding of the context and relevant process to the estimation, which means that both should be performed based on the conceptual model, okay? And well, here as examples of laboratory tests and analyze for material characterization, we can mention several of them, like the granulometric analysis, the mineralogical analysis, the chemical analysis, and also the static prediction test, kinetic prediction test, and leaching environmental assessment of framework. And well, these tests, the laboratory and field testing, they have some limitations. For example, and the sampling, which is related with spatial variability in a site where the geology and mineralogy are variable, and also the long-term evaluation, because the kinetic tests, besides take weeks, they are not able to represent the long periods or of environmental exposure of the material, for example, decades or centuries. And well, basically the results from laboratory tests can overestimate the field weathering rates and underestimate the length of the contaminant generation. So basically, all these limitations, they are related to temporal and spatial scale. Okay. However, despite these limitations, the laboratory tests, they are very important and should be used concurrently with numerical modeling, for example. So the two prediction methods, one does not exclude the other, okay, and they complement each other. Well, but why develop a numerical modeling? Okay. And so one of the biggest challenges in predicting water quality at mine sites is the scaling factor, because how do I transpose the results of my tests to the field scale? How do I go from small to a large scale? How do I go from a small to a large scale? And how can I reproduce the results, which is acquired in the lab, to a structure with tens of meters like a dry stack or a dam? So the Aqueous Geochemical Numerical Modeling is a powerful tool to transpose these results from a small to a large scale. Okay, and the modeling is capable to simulate like the variability of these large scale factors like geology, climate, hydrogeology, gas transport, particle size, and among others. Well, and it's also possible to simulate how these variables affect the drainage quality over long periods. And here we have some other application of numerical modeling. Okay, so using a numerical modeling, we can predict the effluent water quality, like acid drainage, effluent composition in mining waste storage facilities. A numerical modeling is also very useful to validate conceptual understanding and hypotheses. It's very useful to understanding the main reaction between liquid, solid, and gaseous phases. It is very useful to calibrate parameters with less prior knowledge or high sensitivity. And in a numerical modeling, it's also possible to make performing complex calculations, like simulate scenarios, to make the sensitive and uncertainty analysis, and estimate environmental aspects that cannot be reproduced in the tests. Well, but what is a numerical modeling? I like to sentence that say that a model is a simplification of reality, and it's often say that a model is a representation of reality, but it will be more correct to say that the model represents our thinking about the reality. And so the conceptual model can be formalized into the mathematical model, which using chemical principles within a computer code can make prediction and test hypotheses against the results from the real field data. And in this context, one of the most used softwares is PHREEQC, and PHREEQC means pH redox equilibrium. And this software considers the interaction of solid, aqueous, and also the gas phases. PHREEQC is a code developed by USGS in 1995 and is a public domain modeling software, and is maintained and updated by Apelo and Parcus, and currently we are in version 3. So this is a workflow showing what kind of data we use as input data to PHREEQC, and also the modeling output, like what kind of data PHREEQC gives to us. And now we'll explore each part of this flowchart, okay? Starting with detailing and waste rock characterization. So the mineralogical characterization, granulometry data, and density data as well, this will serve as input to my numerical model. It is it will serve as input to my solid phase in my numerical modeling. Okay, so from this data, we can calculate the moles by kilogram of water that my solid phase will represent in my numerical modeling. The hydrochemical characterization is used as input data for the model as well. So we can use data from the environment monitoring, and also in some cases, a specific sampling can be conducted for a better understanding of the area. And we also use a statistic of available data. And with this data, we can develop a conceptual hydrochemical modeling, okay? And we can verify the tendency of mineral to precipitate and dissolve. And the hydrochemical data can be and should be used to calibrate my numerical modeling. And here, the hydrogeological conceptual model of my site will show me the flow conditions. And also it will show me the potential mixing with other waters and also the flow speed, which will give me the residence time of the water in the medium. Okay, so the residence time is a very important parameter to be estimated because it will determine the reaction time between the water and the material. Okay. And here, well, PHREEQC has more than 14 thermodynamic databases, and it will depend on the conceptual understanding about which one can be used for my numerical modeling, and also it will depend on the modeler. Okay, so for example, PHREEQC.dat is the standard database, and however, it is limited in terms of chemical species. And for example, if I have heavy metals, the use of WATEC for F data is recommended. Okay, but if a specific phase for my study is not available at the database, well, we can make the insertion of new phases at phases data block of PHREEQC, or we can make a direct insertion of this phase at the database that I'm using at my model. Okay, but well, how a three-dimensional structure like a dry stack or a dam will be used as input data on PHREEQC. So this is an example of a representative cross-section of a waste rock storage facility. And this is an example of a cross-section, representative cross-section of a waste rock storage facility in which has a variable saturation degree. Okay, this waste rock has an unsaturated medium in the top of the structure and a saturated medium at the bottom. And the water table is here represented by this blue line. Okay, so from this representative cross-section, we can use like a part of this to be representative at PHREEQC. Once the advective dispersive transport capabilities of PHREEQC are derived from a formulation of 1D column. Okay, so we have to go from a 3D structure to a 1D column on PHREEQC. And well, about the saturation degree, why should we consider this different saturation degree? And it has implications for what? So this different saturation degree has different flow rates, okay, which implies in the discretization of my numerical modeling. Okay, so the number and length of cells that I must consider on PHREEQC. And another important aspect about this different saturation degree is the diffusion of gas phases, like O2 and CO2. Well, and speaking about this aspect, what we know and what we should consider about gas diffusion. Well, the atmospheric gases, as example, O2 and CO2, they are transported by diffusive and advective process, which varies according to the depth and degree of saturation of the medium. So the log of partial pressure of O2 at the atmosphere is around minus 0.67. And in the subsurface environment, the O2 can be consumed due to the degradation of organic matter, sulfide oxidation, and other reactions. Well, and according to the literature, the diffusion coefficient of O2 is around 5 orders of magnitude lower in water than in air. But how this dynamic change in a variable saturation medium, for example, a dry stack? Well, we know that the gases, they are transported through diffusive and convective flows. So the entering of O2 in a structure can be in two ways, diffusion and advection. But at the same time that this ingress occurs, there is a consumption of O2 through oxidation reactions. So the O2 ingress by a rate, and it is consumed by a different rate, okay? And these different rates result in a profile, while the log of partial pressure of O2 vary according to these reactions and depth until reach an anoxic medium. And this profile was elaborated to an unsaturated medium, which means that even in a medium with an absence of water table, an anoxic medium can be reached. Okay? And well, still speaking about gas diffusion, here we have an example of CO2 in an open and a closed system. In an open system, there is a constant supply of CO2 that will occur through exchange with the atmosphere, plant respiration process, while in the closed system, all CO2 is retained and consumed in the carbonate dissolution process. And here, finally, after speaking about gas diffusion, so what are the main differences between a dam and a filtered tailing and waste rock storage facilities, like a dry stack? Well, the dam has a predominantly saturated medium with limited O2 diffusion, which can form like a reducing medium, while the dry stacking has an unsaturated medium with atmospheric interaction, which will possibilitate the gas diffusion. So the main chemical reactions in the environment are controlled by thermodynamic equilibrium and kinetics. And explaining in a very simple way, in a closed system with no inputs or outputs, the chemical reaction will tend towards a state of equilibrium, okay, where all concentration of solutes will be stabilized. And there is an equilibrium condition for this reaction, defined by the relationship between the activities of each component and the equilibrium constant K. So here, giving an example, okay, let's consider the following thermodynamic model. Let's consider that the reaction, they are governed just by thermodynamic equilibrium, devoid of kinetics. So we have an initial solution with unsaturated chemical composition relative to fluoride. And this solution is in contact with fluoride, and the fluoride content is sufficiently high so as not to be a limiting factor in this reaction. So this solution will instantaneously, disregarding time, dissolve a significant amount of fluoride to reach the thermodynamic equilibrium. And in this case, the solution will pass through a substantial increase in dissolved concentration of calcium and also fluoride. Well, but is this valid for all chemical reactions? Actually, every reaction has kinetics. In other words, it takes some time to reach the thermodynamic equilibrium. And the numerical models will, without kinetics, the simulation every reaction instantaneously, which is okay if the reaction has fast kinetics that could be ignored, but it could overestimate the capacity for acidity generation, neutralization, and release of ions from minerals. Well, and here we have a very simple example of pyrite solution with and without kinetics. So in this simulation, considering only thermodynamic equilibrium, the solution occurs like at the first step of my simulation, and the results display pH of 1 and extremely high concentration of iron and sulfate. Okay. On the other hand, if we consider a solution rate of for pyrite, the simulation results display a pH of 2.5 and considerably lower concentrations of iron and sulfate. So in our understanding, for the development of a good aqueous geochemical numerical modeling, the use of kinetics is essential. And well, the solution rates of the minerals were extracted from the international literature. And we are always looking for updated materials to use in our models. Well, and here we have an example of rate of mineral dissolution for calcite, okay? And in which K1, K2, and K3 are temperature-dependent parameters, okay? So, and also the rate of mineral dissolution depends on the superficial area of the mineral, the mass of the mineral in moles, okay? And it also depends on the activities of H+, CO2, and water, okay? And well, the calculation of reaction moles occur in a time interval considering the scale factor. Well, and sometimes the equations of rate mineral dissolution, they have parameters for acid, neutral, and basic solutions. And based on the knowledge of my study area, I can simplify these equations considering only neutral parameters, for example. And if my numerical modeling has a considerable number of minerals, this simplification can optimize the computational effort. Okay, and if we have the rate of mineral dissolution, we also should consider the rate of mineral precipitation. And here we have, as example, again, the calcite with very similar parameters considering the rate of mineral dissolution. Okay, and here we have a very simple example of the difference between precipitation of calcite considering thermodynamic equilibrium and considering kinetics of precipitation. Well, as a hydrogeological model, the aqueous geochemical modeling also must be calibrated. And in this case, we must consider the concentration acquired in the modeling, comparing with the field observation. And well, in this specific case here, we consider for calibration the solution percolated by the dry stack in contact with the atmosphere and precipitation of carbonates and amorphous iron-3 hydroxide. And also, an aqueous geochemical numerical modeling allows the simulation of what-if scenarios and evaluate these results in terms of effluent quality, chemical and hydrochemical stability, chemical clogging of drains, generation of acid drainage, attenuation capacity, among others. And here, I'm going to discuss a case study considering iron ore tailing in a very common contest here at Quadrilátero Ferrífero in Brazil. So in this contest, in oxidizing medium, the hematite, which is a very common mineral at iron ore tailings and also waste rock at Quadrilátero Ferrífero, is stable. Okay. So, however, as a degree of saturation increased from top to bottom of my dry stack, the diffusion of O2 will be limited and a reducing medium will be formed. So the hematite will destabilize, releasing trivalent iron into solution. And the reduction of trivalent iron in turn will produce bivalent iron, which has a greater solubility in water compared to trivalent iron. And at the bottom of the drain, there is a greater exposure to atmospheric conditions comparing from the bottom of the dry stack. So part of the dissolved iron oxidizes, forming colloidal precipitates with an orange coloration, which is typical of amorphous iron 3 hydroxide. And well, here I will present another case of study, which was the application of lime to iron or tailing. And this case of study is very interesting because we have results from both laboratory tests and also the numerical modeling. So, well, in this context, considering a closed system to CO2 in chemical equilibrium with lime and portlandite, the results of my simulation display a results of pH of 12.37, okay, for this reaction. And the static test, the phase pH, display results of pH of 12.26, and the kinetic test display a pH of 12.14. So the results were very similar in the numerical modeling and also in the static and kinetic tests. And also here, in the same case of study, we consider an open system to CO2, which means that this material is in contact with the atmosphere, okay? So an open system to CO2 in thermodynamic equilibrium with lime and portlandite with the presence of oxides and silicates, which means that now we are going to have silica and alumina in the system. And the results of the numerical modeling display a positive saturation index for minerals, which means that these minerals, they are super saturated in the solution, like gismondite or bermorite, calcium neutronite, and andradite, okay? And the mineralogical analysis of this material indicates formation of calcium silicates, calcium iron silicates, and also calcium aluminum silicates, which can be interpreted like bermorite and also gismondite. So notice that how the model in this case reproduced what was found in the laboratory tests. And well, this understanding was fundamental and allows the long-term simulation of a dry stack with application of lime to iron or tailing mixed with lime, okay? And this is a very good example about how the laboratory and modeling should be complementary, okay? Well, so now speaking a little bit about some tools that we are using for our numerical modelings. So here we have PEST, which is acronyms for parameter estimation. So PEST is a software package that allows, among other functions, to calibrate uncertainty parameters in a numerical model based on observed data. And this tool is rarely used in aqueous geochemical numerical modeling, but it has a great potential. And actually, we are developing the utilization of this powerful tool in our numerical modeling, considering the estimation, prediction, and regularization modes. And FreePlot is a tool that allows performing multiple simulations in PHREEQC in a loop and generating advanced graphics. Okay, and well, here finally, I'm going to speak about other applications of aqueous geochemical numerical modeling. And as first example about the applications, the chemical clogging. So the output of the numerical modeling gives to us the precipitate of minerals in moles by kilogram of water. And using data like the geometry and porosity of the drain, is it possible to calculate the chemical clogging? Another very interesting application of the aqueous geochemical modeling is the possibility of quantification of the rate of CO2 captured during silicate weathering. So we are exploring in our numerical modeling the carbon capture and storage. Okay. And in the context of wastewater and water quality treatment modeling, is it possible to simulate the addition of chemical reagents, mineral precipitation, and also make the integration between process and treatment? And other application is the mass balance associated with water balance, which allows the flow rate and concentration determination, the possibility of including information about chemical reactions, greater control of production and treatment process, and an integration between process and wastewater treatment. And here, another very interesting application is the contaminant transport model using PHREEQC and also FIFLOW. So here we have an example of a model with and without phase and equilibrium and particle tracking. And well, here another very interesting application is the reactive transport modeling, which is using FIFLOW and PHREEQC. And we have a great whole webinar about the subject in our YouTube channel. So in this specific model, we make the estimation of variation in the reserves of a brine deposit. It was possible to simulate flow and reaction couplet. Okay, and so this integrated flow and transport model was made using FIFLOW and PHREEQC through the PyChem plugin. And in this model, each node in FIFLOW was a different PHREEQC model. And as a conclusion of this presentation, the advanced aqueous geochemical modeling considers many aspects like hydrogeology, thermodynamic equilibrium, kinetics, mineralogy, geology, hydrochemistry, partial pressure of gas phases, and sensitivity and uncertainty analysis, among others. So, thank you very much. And well, we are ready to take questions.